Hello, shall we start? Am I audible?
Yes, ma'am.
Okay. Good evening, distinguished faculty members, esteemed organizers, and participants. It is my privilege to welcome you to the third day of the Faculty Development Program, jointly organized by the All India Council for Technical Education and Majlis College. Today, we proceed to the fifth technical session of this FTP. The session will be conducted by Dr. Rashmi P., Senior Project Engineer at the Indian Institute of Technology, Kharagpur. Dr. Rashmi is currently leading the AI and ML Technology Innovation Hub, a project funded by the Department of Science and Technology that focuses on the development of AI-enabled wireless links for highway vehicles. She earned her Bachelor of Technology in Electronics and Communication Engineering from the University of Calicut, where she was a recipient of the Prime Minister's Scholarship. She pursued her Master of Technology at the National Institute of Technology, Calicut, supported by an MHRD fellowship. Her doctoral research was undertaken at the Indian Institute of Technology, Madras, during which she was honored with a Qualcomm Innovation Fellowship worth rupees 10 lakh. So, on behalf of the Majlis Group and all the participants, I extend a warm and heartfelt welcome to Dr. Rashmi P. We are delighted to have an eminent professional of her caliber lead this session on AI on the road, opportunities and challenges in autonomous driving. We are confident that this session will provide valuable insights and foster enriching discussions. Thank you. Rashmi ma'am.
Hello?
Yes, ma'am.
Hello?
Yes, ma'am.
Am I audible?
Yes.
So, thank you for the kind introduction. Is there any problem with my sound?
No, it's okay.
It's good. Okay. So, thank you for the introduction and inviting me for the talk. I'm very much privileged to be invited for this FDP program. And a warm welcome to all the faculties, research scholars, and the industry personals who are present here for the talk. And I extend my extreme gratitude to each and every member, organizer of the program for the smooth transition and the talk availability. So I welcome you all to the talk. I'll share my screen. So is this visible now?
Yes, ma'am.
Yes.
Okay, thank you. So the topic that I have taken for today's talk is the AI on the road, opportunities and challenges in autonomous driving. I'm extremely happy to talk about this topic because it is very relevant at the point of time. And also it is something that works, that can be grown only with AI. So I'll move on to the talk. So I'll be focusing this entire talk based on the autonomous driving perspective. So autonomous driving refers to vehicles that can sense the environment, that is basically the road environment, understand it, like how much traffic is there, which route is possible, and drive with minimal or no human input. So it is basically referring to self-driving cars. So I think the topic is very much aligned with the FDP objectives. First of all, when we look into the AI domain, this topic, that is the self-driving car, it is an integrated subject that takes into account multiple topics in the AI domain, like computer vision, machine learning, deep learning, and many other topics, also data science. And then it also is a problem that showcase how these technologies needs to work together to make a real-time good decision. And next thing is that it has its own academic relevance because it is a real-time example of applying AI ML to a physical problem. Like it is something that, as I'm coming from an electronics background, as ma'am said, so there are problems with AI that we try to solve in the software domain. However, this problem is different from that because it has a very real-time result. Also, there are a lot of practical challenges because there are a lot of limitations in the sensor point of view. Like a car needs to see everything that a person needs to see. So there are sensor limitations, data quality issues, safety concerns that need to be addressed, which only will deal to a successful deploy of autonomous driving system. And also it is very much aligned with the national education policy and OBE principles that it promote the hand-on experience that prepares students to solve real-world challenges. So the problem is very much relevant that you can see the number of startups and companies that are trying to solve this problem and trying to form an autonomous driving system. So as I said, it is always focusing on a self-driving car. So a self-driving car by itself has it requires a lot of core capabilities. So first thing is the perception. That is the first and foremost peripheral level. That is how it sees. That is what a human do, right? Like first it will see and then only our brain will process it and make a decision. So first thing is the perception, where the machine or the car should detect the lanes, that is the road boundaries, then what all are the vehicles around me, whether there is a vehicle very close, so whether I can accelerate, decelerate. So that decision needs to be done based on the understanding of a vehicle. And also sometimes the vehicles are not oriented, like it may not see the bike as in a particular angle, it may be sometimes tilted, it may be in an overtaking direction. So those kind of understanding need to be there for the vehicle. And also pedestrians and traffic signals. So, and signal boards, sign boards, everything needs to be perceived at the first level. So that is the first level peripheral capability of an autonomous driving system. The next will be localization. So it perceived in the first stage, like where I am in the road, like whether I can, in the lane boundaries and whether vehicles are close by and something. But apart from that, it should know in which position I am, like in the global coordinate, in which XYZ direction I am, the XYZ position I am, and also in the local road coordinate, where is my position. That and all, it requires to be known because then only it can plan its path as the next step. So the next step is planning. Planning is like once you perceive something, you know your location. So I am in like this part, I'm in Kerala. So I'm following this path. So which is the lane that I should follow? I'm going from to Guruvayur temple means what should be the path that I should take? What will be the maneuvers? Whether I can take an overtake, whether I should follow a bridge, whether I should make lane changes. So that kind of planning will be the next step. So these things I told, the perception, localization, planning, all these are like kind of software domain side. But once these decisions are done, next part is the main control level. That is executing the steering, smooth steering, braking, acceleration, turns and everything according to the received perception, localization and planning. So it is indeed a multi-stage process. And then why we need autonomous driving? So the first and foremost reason why we need autonomous driving is to improve the road safety. So as per the study, the statistics that is available in 2025, about 90% of the accidents that happen all over the world is due to human error. So if we have a fully automated system that works like the machine do the every driving kind of thing, it will of course provide improved road safety. And also it will reduce the traffic congestion because it will be kind of a corporate driving. Like I'll be following my route and there will be an optimal velocity that I'll be using. There won't be like another, if there is another autonomous driving that is going on, it kind of like plan together to how to move it without traffic congestion. And another important advantage is the increased mobility for non-drivers and those with disabilities, and also for elderly people, students, like picking up, dropping students and everything. And of course, as the result of all this, a byproduct will be the enhanced fuel efficiency and lower emissions. So that is the main advantage of autonomous driving. It is supposed to increase the road safety. So before going to the depth of autonomous driving, first I will say what is SAE level. So SAE stands for Society of Automotive Engineers, who makes the standard for the automation levels. Like it has divided the entire vehicle groups to 6 levels, that is starting from L0 to L5. L0 correspond to the group of vehicles that have no automation, like completely mechanical kind of driving. So as you can see here, that is mentioned, it is zero autonomy. The driver is supposed to perform all driving tasks. So that are the manual cars that we had. And L1 means there is some driver assistance. Even though it is low level, there are some assistance. So it is completely controlled by the driver, but some features like say the cameras for parking and everything. So such small level of driver assistance will be there in L1. And L2 means from L2 and above, there is some partial level of automation which will reach full automation at the level of L5. So at L2, the vehicle has combined automated functions like acceleration and steering. So acceleration and all the vehicle will kind of do. However, the braking and everything is the driver's problem. So the driver must completely remain engaged with the driving task. He is not going to like sit idle or something. He has to do the braking and everything. However, some functions will be there that the car do. And the fourth thing, that is the L3, the driver is a necessity in this level as well, but is not required to monitor the environment. Like he don't have to see around, but he should be able to take the control when the vehicle is like in specific conditions or something, the vehicle should take the control. The driver is a necessity. Like you can't drive it without a driver, but there are it kind of like it reaches the fully automation level to some extent. And L4 is the high automation. Here, the vehicle is capable of performing all driving functions under certain conditions. The driver may have the option to control the vehicle, but it is not a necessity to have a driver. So L4 and L5 is like no driver situations are possible, but L4 is under specific condition, like in a specific area or something like that. Sometimes it is like an industry level, the picking and dropping of their raw materials within a compound, within a campus. That kind of high automation is what L4 indicates to. And L5 is the fully automation, like the vehicle is capable of performing all functions in every condition. The driver may not be there and driver can take control if needed. So according to the SAE levels, these are the different car companies that produce different cars in different SAE levels. The cars that are available in India are mostly in the SAE level 0 to 1. The major car companies that are working in India are in 0 to 1. Some cars have features that comes in L2, like Mahindra, Hyundai, and Kia. And these are the data that I got from like Google and their website. So they have the basic ADAS and alerts and the partial assist monitoring and all in the 0 to 2 category. However, L3 and above are some like some companies like Mercedes-Benz and Honda say that conditional autonomy and handover is possible. And L4, some taxis are there like Waymo, Cruise, and Baidu. Baidu is in China. Waymo has service in many US cities. So these are like driverless taxis that are available. They are robo taxis, but it's kind of like they work in a particular area only. That is, that map is stored in the car, and based on that route map only the car is moving. So there is no L5 level cars yet. So the full autonomy goal is not yet achieved. One thing that I would like to point out is that Tesla, which is supposed to be one of the biggest autonomous car companies, is still in L2. So there is a lot of scope of research and lot of scope of bringing in AI to all these fields. So the first figure here is the Tesla full self-driving system. So even though the name is full self-driving, it is still in the L2 stage. The driver need to be ready like that. So as shown in the photo, it is the real by photo. And the driver needs to keep his eye on the road. So that is what the company demands. It is not fully automated. And immediate takeover capabilities are required. Like if in case there is an accident, it is not like the company is going to own it. It is always the person's responsibility. And the right one is the Waymo car, which I told as the L4 car. This is the vehicle. This vehicle can drive entirely by itself, but in a particular region. No human driver is required and limited cities. And also the other thing is it is very slow. Like the speed limit is 30 to 70 kilometer per hour, but the statistics show that like majorly in the town and all, the speed that usually it achieves is 20 kilometer per hour. So it is kindly slow, but very safe. Waymo has no much reported accidents yet, but Tesla has around 50 to 51 fatal deaths in the as reported in 2025. So where do we stand in terms of SAA? Like where do India stand? So as I said before, most ADAS equipped Indian cars are in SAE 0 and 1. There are features that are available like lane departure warning, forward collision warning, basic lane keep assistance, and adaptive cruise control, like how to apply the acceleration and everything. However, braking is in the hands of the driver. So that is the most ADAS equipped Indian cars that we use are here in the level of L0 and L1. However, a few premium vehicles support L2. So some examples that I could find in the internet are Mahindra XUV 700. So it has some L2 features, MG Ester, MG EV, Hyundai, Kia, BMW, Audi, Volvo, higher end models, etc. So they have the lane keep and lane centering feature. Also, they provide the traffic jam assistance. Here, the car can steer, accelerate, and brake also. Like in L0 and L1, braking is not there. Here, braking is also available, but driver must supervise. So even though we say it is 0 to 1 and 2 in India, these are one very anticipated projects that are in India. So the first one is the complete driverless car. So this report came in Times of India last month. It is a collaboration between Wipro, Indian Institute of Science, and RV College of Engineering. And they have given rise to a driverless car named Wirin, a self-driving car built entirely in India. So it is made in the Make in India campaign. And this taxi was tested in Bangalore city for a short period of time. And it was successful. So it is one of the emerging and very like completely made in India project that we are able to achieve. And it is an L4 level SAE automation. That is what is claimed. Similarly, another thing is the test drive of the autonomous driving by Swayat Robotics. So that is another company based in India. And they have developed their system on Mahindra Bolero and test drive in Indian like rural area and urban area as well under a speed of 30 kilometer per hour. So you can see this is a snapshot taken from video from YouTube. You can see the entire 10-second or 20-second video in the YouTube. So you can see people standing around, there is rickshaw wala and also the trolleys, everything. But they could actually complete the entire run through the road. So this result is actually 1 year before. They might be very much like advanced in terms of technology now as well, but that their results are not available in the website. So even though we don't have L0, L4 level of cars now, but we are in that stage of developing. Okay. So once we understand the SAE level, we can understand how much AI is required. So L0 and L1, that is the lowest level, they have very little or no AI. It can work on rule-based ADAS. Rule-based in the sense, if you say this happens, then this should be the how the system should perform. I can actually code it based on that. If there is a vehicle at this distance, reduce the vehicle speed to this level, like that. It's a rule-based system. However, L2 and above here means it requires some basic AI. It needs some reliable perception. So it's like parking assistance, when you have to, the 3D 360-degree camera, that and all comes in the L2 category. Here the vehicle can steer, accelerate, brake. And however, the responsibility still lies with the driver. L3 and above means it requires strong AI tools. It requires perception, prediction, and planning. It should understand the scene, predict the other vehicles present in the area, their velocity kind of, and make decisions. It handle mergers like merging of lanes, cut-ins, the extra left cut-in, right cut-in, etc., and also the obstacles. So no rule-based technique can do this. So the role of AI in autonomous engineering will be to go beyond SAE level 2. Main role, like if in case we want an impactful change, AI should come in and very good AI algorithms needs to be developed. So the vehicle must replace the human perception and decision making, which is possible only through AI. As SAE level increases, AI becomes the core driver of autonomy. And why it is challenging? It is quite obvious that the environment is quite complex. We know how our roads are, we know how our environments are. So there is no cut and right rule like this is the condition that your car is going to work. So it is so complex, so evolved, very much changing. And also the other thing is high performance requirement. This autonomous driving is a very safety critical problem. Like safety is the first thing that needs to be addressed. So the performance requirement, even like you can't expect a millisecond delay in the performance delay, something like if in case you want to brake now, it should be like that now. It can't go a millisecond later. So that is why it is very challenging. Also real-time computation. The computation speed that the car should do, it is very high. So all this computation needs to be done with a battery backup. So everything is need to be, it makes the problem very much challenging. And when we look into India, the special requirements are there because of the traffic chaos, mixed road uses, and the weather. So I think I have explained why AI is very much important for autonomous vehicle. Now I'll quickly, in a peripheral level, go through the autonomous vehicle technology stack and explain each block to a minimal level and explain why AI is important in each of these and what AI can do in each of these blocks. So the autonomous driving system can be broadly classified like this. Like the first stage will be the sensor stage. So sensor will be like the vehicle sensors will be there. There will be camera, radar, LiDAR, ultrasonic, and GNSS sensors. So all these sensors are like kind of the eyes of the vehicle that helps it to see what is happening around. And once it is done, it goes to the perception level. Like it saw something, now it goes to the visual cortex and it will be processed by the brain. Like what is the vehicle of my nearest vehicle, the nearest vehicle, what velocity it is going through, what is the location of the nearest vehicle, whether there are some stones or some boundary walls, the objects need to be detected, classified, and whether those objects, if some animal is crossing, it needs to be tracked, and all this perception will come as the next stage. The next will be the prediction stage. Like based on the sensing and perception, it should go to the prediction in the sense what is the plan route that it is supposed to go and everything. And then it is the control stage. Control stage is the last stage where all the things that it got, it's taken into the brain and the decisions that we do with our hands, like turn the steering to the left, right, speed up, speed down, provide acceleration, provide brake, that kind of stuffs will come in the control phase. So the sensor and the control are basically the hardware side, while all the in-between stages comes in the software. So first we look into the sensors. As I said, it is how the self-driving cars see. So there are a lot of sensors in the self-driving cars. The sensors are like long-range radar, short-range radar, camera, LiDAR, and many others. So this down here is a Waymo car structure. Here you can see where are the radars and cameras and everything placed. So it is like they have 8 number of LiDARs and radars and everything. Each radar and LiDAR have its own functions. So the long range radar actually helps in the adaptive cruise control, like how to accelerate, decelerate and everything, collision warning, highway long range detection and vehicle tracking. And short range radar means the range will be small of that radar. So it will be detecting and trying to form images of the objects that are very close. So blind spot detection, cross traffic alert, parking assistance, that and all comes in the short range radar. And camera, it is lane detection basically, and the object classification, whether it's a car, it's a bike, it's a truck, that kind of classification will be there. And traffic sign recognition and traffic light detection and everything. And LiDAR, it is a kind of radar, but it works with light waves. So it's like when the visibility is low, the camera won't work. So LiDAR is the one that helps at that point of time. It finds the distance estimation and localization and high resolution perception is what LiDAR. So Waymo, in this car, you can see this top one is a LiDAR. They have 4 to 5 LiDARs that are working. And in Tesla, they are not using LiDARs and radars. All that they use is cameras. So it depends on the company, how many sensors they use and everything. So Tesla has focused to use only cameras. Maybe the camera numbers may be increased in the coming models. However, they have stopped using the radars and LiDARs in their one. So once the sensors get this information, it's like no one sensor can completely confirm the presence of a vehicle or something. So it is like a fusion of all these data that makes sense. So here you can see the camera is here. So the camera, this pie chart is based on this variables. So you can see it cannot do the distance detection and velocity detection, but it can do very good when it comes to vehicle detection, color detection and everything. Similarly, different sensors has its own capabilities and its own misses. So together, when we fuse it all the data together, we will get a complete image of what is happening outside. So this is not a system redundancy, like one thing can do anything. It is just the union, not intersection of everything that makes sense. So no single sensor is perfect. Fusion only can improve the accuracy, robustness, and reliability. So here itself, it's like at each millisecond, you are getting a lot of data from all your sensors. So how to fuse them is one of the problems that will be there. And even it's not like take this data like that. Sometimes it will be like if you want to detect an object, at least 2 sensors should say yes. So those kind of models will come in at this sensor fusion point of view. So once the sensor data is available, the next stage will be the perception. So perception is like how to fuse the data and then make sense out of it. So low level fusion is there, which combines raw sensor data, like sensor data is there, I combine them and I do that. So it will have highest accuracy because I'm not processing the data, I'm using it as such, and it has the richest detail. However, when you use the raw data, you are getting like GBs of data every second. So how to compute them? There is a timing synchronization that is needed. So those cones also come with the low level fusion. So these are the techniques that are usually used, like Kalman filter, extended Kalman filter. So these are the tracking algorithms and the fusion algorithms that will be commonly used for low level fusion. And this kind of fusion is used in high level AVs as well, because they need that kind of accuracy. Similarly, there is mid-level fusion where there is some features that are fused together to make a better understanding. And there is high-level fusion. High-level fusion in the sense, the sensors make some decisions, like it will get the data, it makes decision, and the decisions are then merged. So the output of sensor is only the decision. It's like a small number of data, and it will be merged. So because of this processing, sometimes the accuracy is lost. So this level of lowest accuracy we cannot expect in L4 and L5 level of highly autonomous vehicles. So this kind of things will be used in L1 and L2 ADAS. Another fusion method is the deep learning multimodal fusion. So this is one of the things that most of the work in research is going on now for the sensor fusion side. Where neural networks are used to fuse the camera, LiDAR, and radar data join. So the neural network kind of understand how to weight the data, which data should be focused at which point of time, and how to merge them to get a better understanding. And also the thing is, why we need deep learning is like, it's not like I fuse the sensor data at this point of time. On this road, if I fuse it at evening 5 p.m., I will get a particular result. That won't be the result at a very high traffic time, or when rain is there, or when the visibility is not clear. Like my camera will be completely blocked at that point. So we need some intelligence in the machine side. It's not like we can do with some models. So neural networks will be very useful at this point of time. It learns complex relationship and the best semantic performance. However, the cons are it needs large data sets, and the training is also expensive. So some techniques that are there in the research stage are multimodal transformers, BEV fusion, LiDAR camera deep fusion and all. And they are supposed to work in the L3 AVAR, L4 models. Another thing is cooperative V2X fusion. Cooperative V2X, I will be explaining it in the coming slides. So the thing is like you will get data not only from the sensors, but from the nearby base stations and the nearby users and everything, like from your mobile or something. So it is kind of an extended perception, like your mobile will also have your GPS and your car is also going to have. So somehow it cooperatively kind of understand and do a strong connectivity and a result. However, there are cons. The connectivity is the first issue. Like you need your mobile to be completely connected. If it is lost, then that added advantage will be lost. And our roads, at least in India, we don't have that kind of infrastructure ready. So whenever we come to the infrastructure-based communication, the infrastructure should be strong. So still, it is one of the methods that is being in study nowadays. At least even if not the entire road or something, at least in a small corridor, if there is a good infrastructure, how we can bring in the cooperative V2X fusion. So here it is always supposed to be there in the L4 and L5 smart mobility, that is a higher level. So one thing is that if sensor fusion is wrong, the entire decision pipeline is going to fail. And perception involves the object detection, classification, segmentation, tracking, and all the processing of the thing. And perception forms the foundation for prediction, planning, and control. So once we perceive what is around us, the next thing will be the localization. Like it is needed for lane level accuracy, required for trajectory planning, and essential for merging lane changes, like to know where I am present. And we all know GPS, GNSS, all these will be used for that. But this GPS, GNSS, it works well outdoors. And also it is unreliable in urban canyons when there is a lot of, you are going under a lot of buildings, and when there is a thick forest, tunnel, dense cities and all, GPS fails. So at that case, what will a car do if it is an autonomous car? So then there should be some backup plans on some very good localization schemes. So that is why LiDAR based localization is there. LiDAR based localization is very accurate, like it gives centimeter level accuracies, and that is why the robot taxis are using that. These robot taxis are providing service in a like in a city area. So that centimeter level accuracy is required. So they are using light. Another thing is visual localization, camera based. So it works where GPS is unreliable, and this is what Tesla is completely focusing on. And Mobileye, that is a company that is providing ADAS features, is completely based on visual localization. And sensor fusion localization is like fuse all the technique and provide a localization. The other thing is the HD maps, like stored high definition maps are available in the vehicle. So those vehicles, for those paths, it will be useful. So these HD maps are used by Waymo and Cruise, the robot taxis. However, HD maps are not used by Tesla because Tesla as a model is not supposed to work in a particular geographic area. Tesla is supposed to work in any region. So the HD maps cannot be saved, and that method is not possible. And still, for this localization also, there are specific challenges when we look into the India geographic area. First of all, we have poor map availability, and we have curvy roads, and the lane markings, sometimes it is there, sometimes it is not there, sometimes it is not visible. And even if it rains and if the road is wet, sometimes it is not clear. So, and GPS is unstable in cities. Like you all would have used GPS and driven through cities. So it is very common to miss the lanes and everything. And we are in a area like we have a many vehicles that are buses, trucks, big vehicles and everything. So sometimes your car is completely occluded. Even there is a roadside infrastructure, it may be completely masked. And that dynamic objects in dense traffic, like you can see a lot of animals also in the road. Sometimes like the machine needs to learn that is an animal. So those kind of difficulties are particularly there in India as well. So once you have the perception and localization, somehow the data is available in the car, right? Like you know where it is, you know what all are my surrounding and everything. The next step your car should do is prediction and planning. So prediction, as I said before, is the vehicle trajectory. In which route should I move? At least not for a bigger time or the bigger distance. At least for some 1 second or 2 seconds, I should be able to tell in which route my vehicle should go. And is there a pedestrian movement around? Like if in case there is a human moving around, what will be his velocity, whether he will reach this point, that and all, that kind of intelligence needs to be there. Then lane change intentions, whether there is a cut in, overtakes, traffic light changes, sudden stops or slowdowns and everything. And planning is to choose safe maneuvers, avoid collisions as early as possible, and reduce sudden braking or swerves. So, and improve the comfort of like that is obviously there. So I have kept 2 photos here. These are some Google images that I got for traffic in India. So we know how our systems are. Like we usually don't follow lanes, and we usually have many times we don't have traffic lights, or sometimes it's like as you can see here, it's congested. So it's very much near to impossible for a humanless driver to even predict a path in this case. And if in case a vehicle needs to do that, it is never possible with a rule-based system. Like where is the rule? So then only it will work, right? So the rule-based systems completely fails with such complex multi-agent interactions. It will miss the agent subtleties and intent. So hard-coded rules are not going to work. So one example that I'll say is the Tesla's phantom braking system. So Tesla was using a phantom braking systems in the year 2021, which is supposed to work based on a rule. So they had their object detection algorithm. If there is an object like this, apply brake kind of thing. But what happened is like their objects, sometimes shadows were there, and sometimes the overhead bridges were there. All these were sometimes taken as objects, and the vehicle driving smoothness was not available. There were a lot of complaints that happened with Tesla. And also the radar that Tesla used to detect the over bridges and everything as some object present. So every time it was braking unnecessarily, and there were a lot of complaints from the customer side, and they have stopped using their braking system based on the model. So now every car company is moving to the AI based system because that is only what is feasible for the autonomous driving. And now, once everything is done, now we want the vehicle to take control, do the steering, that is the lateral control, do move left, right, keep the vehicle in lane, follow curves, minimize lateral error and everything. Also control the speed, like maintain the desired speed and the desired distance, and smooth acceleration and braking. Another major thing is the model predictive control. Like apart from this lateral control, longitudinal control, and everything, every person is going to drive in a different manner. We know, like some people who drive very smoothly, like without making any problems completely in the road, and we know the other extreme as well. So it is like something that individual person-based dynamic. Like we can say it is kind of the micro traffic that the person creates. So that vehicle dynamics also needs to be taken care while making the control. So this manages the constraint, predicts future errors, and produces smooth trajectories. So I have covered all the verticals of the autonomous vehicular stack, and I think I kind of told why machine learning algorithm is important. These points are summarized here. That is, it handles nonlinear and uncertain vehicle dynamics, improve stability under noise and missing inputs, then enable human-like smooth steering and speed profiles, and robust in unstructured chaotic track. So now kind of it's clear that AI is unavoidable and it is so necessary. But which AI model is need to be used in which AV stack? So that also is, there are a lot of research going on. This table is summarized based on many research papers that I have seen. So in the sensing and fusion, as I said before, the goal is to fuse. So the main work is happening in the multimodal fusion network, like how to weight and add this fuse data, how to, in which situation, which thing to be chosen, and whether to avoid a particular result or go based on the majority rule, what should be the process and everything. Also, transformers, which are very high-level AI models, are also used for fusion. Then deep sensor fusion is used. So these are some of the models that comes in the sensing and fusion domain. And when it comes to perception, it is understanding the scene. Here, the study is mainly focusing on the CNNs, that is convolutional neural network, then RNN, recursive neural networks and everything. Because there is always a dependent data that you are getting. Dependent in the sense, like whatever data I had at time 1 second, after 5 minutes, after 2 seconds, at time equal to 3 seconds also, I will be having some data related to that. Like if in case I move the lane little bit, I'm going to be in the next lane, some kind of that. So how this dependent data needs to be processed, so that and all will be very much useful when CNNs are in the picture. Also for object detection, YOLO, retina net, sender net, more image segmentation and those kind of algorithms are used. And for prediction, LSTM, GRU and RNNs are used for the same reason I said before, like time series modeling is possible. Time series in the sense it's dependent. It's not like I am at 1 second in first lane and I'm at second at the 8th lane. I will be in the first or second lane. So that is the kind of time importance. and transformers and graph neural networks are also used for prediction. And planning, usually reinforcement learning is used based on the the data and the previous behavior. It needs to make the decision of where to follow the route and everything. And there are also hybrid deep learning planners that are suggested in the literature. And in the control side also, TRL algorithms, neural network, everything is suggested. So there are a lot of research going on in each of these verticals with a lot of AI coming into the picture. Mission, computer vision is coming, data science is coming. So it's a merge of all these schemes that is coming in. So a person with a good understanding of each only can suggest a particularly good model that can work in each of us. However, even if we say AI is important, AI is unavoidable, everything, there are many issues and challenges and complexities that comes in. First thing for any AI problem is the dataset complexity. It's petabytes of diversity data needs with rare events and Indian routes. It's like every second you are going to get different types of data in very large number of quantity. How to handle all this data in the best manner. So, and as an autonomous vehicle, all this data needs to be stored in your car hardware, right? And this the processing speed, so that high level processor needs to be present on the car. So that computational cost is there. It will be very expensive. Then long tail and rare events like uncommon high risk scenarios will be there. Sometimes like a tree branch falling down. It is rare event. Like sometimes a cow is crossing. So those rare events, it's like some algorithms you can completely neglect the rare events, but this autonomous driving is such a safety specific application that you cannot miss out these rare events. So that is one of the major challenges. If the algorithm is not trained for such events, how such a car will behave in such events is unpredictable, and that cannot be, that is not acceptable. And the robustness and generalization, as I said before, weather, occlusion, sensor noise, all these are going to vary. And interpretability and safety, which is very important. Then data time deployment challenges, like it has very less latency. That is, the action should be taken in millisecond delays. However, every processing should be done in a quick second. Another AI model that is proposed is the end-to-end learning. That is a single neural network maps sensor input to driving action. So till this point, what I told is like in each of the vertical, we will have different network. Each output is going to the next network like that. Instead of that, end-to-end from the data point to the action point using a single neural network, the number of layers will be moved. It needs to be modeled and weighted accordingly. And so it learns human like driving from data. It's like it's a merged way of understanding the entire thing. Like you cannot from the neural network understanding or something, you won't understand how it is merging the data, how it is going to perceive and everything. It is just like input output and a black box. So it avoids handcrafted rules in chaotic traffic. Like it's just like a generalized rule. Captures subtle cues, pedestrian posture, wheel angle, road texture, and everything. And it simplifies the architecture. You don't have to go to each block and see whether this performance is good, check the validity of each performance and everything. So it is a simplified architecture and it provides a strong generalization. However, it is not explainable, as I said. Like you don't know if in case it is not working, you don't know which one didn't work or where you should improve or which data is the one that I should modify, or that kind of understanding is very difficult at this point. So end-to-end learning is another domain of work that is happening. The methods that these people mostly use are the imitation learning, RL, vision transformers, and control heads. So when we compare these two, each has its own advantages. The modular AI architecture that is using an AI architecture for each of the modules. It is interpretable, transparent reply, easier debugging, and it requires less data compared to the end-to-end modules. Also, it supports strong safety validation and verification. It provides complex integration, and handcrafted rules fail in chaotic traffic. So those things are the disadvantages that comes with modular AI, and it comes with the end-to-end AI as well. However, end-to-end AI has a simple architecture. It's like input, output, and a black box, as I said before. And it learns human-like driving from real data. So that is what is being claimed in the literature. And it handles unstructured traffic effectively. However, it needs extremely large training data set. Like it needs to be trained for almost every conditions, almost every weather, and almost every traffic scenarios. And it is very hard to interpret and debug, and it is difficult to certify safety due to black box behavior. Like how you will give a guarantee that it is going to work provided this thing happens. So that kind of situation is particularly difficult with the end-to-end AI structure. So the modern autonomous driving schemes blends both the worlds. Like they need a modular AI structure, parallelly they will have an end-to-end AI structure. The modular stack gives the interpretability, safety, and reliability, and end-to-end learning for adaptability, human-like driving, and unstructured environments. So it is like for some of the control actions, you need the end-to-end learning, and for some of them, it's to use the modular stack. So those kind of research papers are also there, and it's very recent that is happening in the autonomous driving. So the next question is, as I said, the first stage or the peripheral thing is what sensors give us. Now, is there something else that we can? So the decision making by sensors alone has a lot of led to lot of accidents. So these are the results that I got from this paper that is cited below. So on May 7th, 2016, a Tesla Model S crashed into a side track of Florida and killing the owner. So according to the Tesla's explanation in the court, the camera was blocked from sight due to the car corner. So it is completely the loss of the sensor data that got into the crash. Although the sensors equipped on one of the Uber's car detected the pedestrian, the software system decided that no immediate action is required. So that is even more dangerous. Like even though so that is a problem in the perception level. Even though it detected the pedestrian, no action was taken, which led to the death of a woman. So it can happen that you can't completely trust on the sensors. So sometimes sensors are incapable of detecting traffic jams or accidents. That is another condition. Like it cannot say like traffic jams are or accidents are there in the end of the road. Sensors have a capability of few meters. I can't say after 2 kilometers there is an accident going to happen something. So the shortcomings of the sensor need to be remedied by equipping more sensors. However, this more sensors means it is going to be more expensive, more data, and like it is the growing trend only, but still there is a limit for the increase in the sensors and everything. So what comes as a lifesaver at this point is the networking and communication technology, which can greatly make up this deficiency. Like what is this networking and communication technology is like, instead of completely relying on what the car sees, give the data to the car from the nearby base station. So now we have the 5G, 6G and everything. We have the freedom of implementing roadside units. Roadside units are a smaller version of the base stations, which can be completely dedicated for vehicles. So if such roadside unit enabled enabled roads are there, the data can be transmitted from this roadside units to the car and give information regarding the block after some time. And this data will also add up to the sensor data. So it will become more reliable, feasible, and efficient. And the information shared in real time among numerous vehicles such as location, speed, and road state can be adopted as the input to the perception layer. That is like the car will be driving not only based on its data, it will be based on the data that is coming from a vehicle that is going some half a kilometer back front. So it's like somehow that vehicle can be used through the base station. That data can be used to tell me that after 1 kilometer there is a block, don't use this route, take a right and a turn. So when we look into the communication perspectives that is available for autonomous driving, it can be classified as this. So V stands for vehicle. So V to V is vehicle to vehicle communication. V to I is vehicle to infrastructure. Infrastructure is the roadside unit or the base station, something like that. Then V to P is vehicle to pedestrian, like communicating with a pedestrian or a person walking at the side of the road. Like his mobile can transmit the data to me. And vehicle to network, vehicle to cloud, vehicle to home, vehicle to grid, vehicle to X. Like V2X is the umbrella term. We say V2X means vehicular communication. It can be with anything. So all these things are feasible and are standardized in 5G itself. So 5G has its particular protocol and the frame format how to transmit for each of this. So these data can be very well implemented with the roadside unit or the base station itself and the car. So that data is very important for autonomous drive. It reduces the reliance on perception only systems, that is the sensor only system. It extends the visibility beyond line of sight. It enables corporate driving, like corporate driving in the sense it is not like I am driving my car. It is like this many cars are driving on the road. It's like cooperatively, if you are going to accelerate, I'm going to slow down. It can be sometimes used for battery management as well. Like if in case there is a battery drain for a particular car, if in case corporate driving is available, like the person in the front can move a little bit so that that car can reach the next charging station also. So it improves the prediction accuracy and it is critical for Indian roads with occlusion, blind spot, and unpredictable traffic. So that is how communication can back up the autonomous driving. However, it requires that kind of infrastructure as well. And this is the picture of the road that we know. So if you can see, like suppose we have a roadside unit here, like a lamp side, it is a lamp post, and if we have a roadside unit here or an antenna here kind of thing, it is not like it is going to communicate with one car. It is going to communicate with all these cars. So the kind of problem with the communication is also not so simple. It requires ultra low latency, like the same latency that autonomous driving is extensive. And by ultra low latency in communication field, we expect the latency to be 10 to 20 milliseconds. So that is a very large value actually. For safety instructions, like to if there is a crash, you are giving a safety instruction to brake to all the vehicle in the area, means it should reach in the standard says such messages should take no longer than 1 millisecond. So that kind of latency to this many cars, this much data, so that is a very high problem to solve. And also the reliability. If you send the data, it should be 99.999% reliable. These are the standard specific V2X communication scenario values. And the high data rate, like the LiDAR data, the GPS data. GPS data is fine. The LiDAR data, the camera data, the map data, if the cars send it to the roadside unit or the base station, it's going to be a large amount of data. And if it needs to be shared among the other cars, like this car is coming from this direction, that the location of another car needs to be shared and all, means the data rate required is very large. Also, the communication needs to be supported for the mobility. Like if the car is moving, the signal need to be sent in the new direction. Similarly, it needs to be scalable. 100 plus vehicles can be happening at the can be running simultaneously on the road. So it needs to support, the communication needs to support that many cameras, vehicles. Then security and privacy, like when you are sharing the data of one vehicle with the other, if somebody is going to use this data. So those kind of hacking security is must. And interoperability and network coverage is another problem. So the vehicular communication can aid it. However, solving the vehicular communication and supporting an autonomous has its own challenges. So these are some of the problems that comes in the vehicular communication. First is the beam management and beam selection. So it's like what beam management means, like where you point your signal. So this is my research area. Actually, what I'm working on is this part. So AI learns patterns of vehicle trajectories, angles, speed, blockage, which is essential for the millimeter wave, that is the 5G signals. So AI is required because it kind of understands where the vehicle is moving and it avoids the blockage of the signal. Somehow understand that the vehicle is going to be occluded by the track. So like kind of send the signal that it should follow this path for the next 1 second. You are going to be behind a truck for 1 second, use this path. So this kind of intelligence can be brought in only with AI. Another thing is spectrum and interference management. As I said, it is like multi-user communication. Many vehicles needs to be supported. So the entire bandwidth need to be divided in a logical fashion. Also, when you communicate with many vehicles, there will be interference. So that needs to be managed. Then operative perception, like the how to bring in the camera, LiDAR, radar data to the roadside unit, base station, and give feedback. Like you are going to have a blind spot at this point. There will be it can also verify whether the car is perceiving the data correctly. Like if it is sending the RSU its location, it kind of can understand whether it's the correct thing, whether you can follow the route and every kind of thing. Then the channel estimation prediction, it is basically a wireless communication topic, like how your environment is moving. If there is a velocity change or acceleration change, the signal needs to be sent in a different fashion. So how that is going to be there. So those kind of things also is needs to be addressed using AI. This cannot be done using a model. Another thing is security. Sorry. So without AI, we can what we will have is like there will be poor performance at high speed, and there will be no prediction of blockage or something. Like your base station will be losing its energy in a particular direction while you were not able to get any signal. Then very limited support for wave mobility. Wave stands for millimeter wave. So millimeter wave or the 5G high frequency signal, this signal fades very quickly. So if you are going to move to a new position, you won't get the signal. So if in case you are going to a new location, your signal needs to be transmitted in that direction. So those kind of information AI is required, and it cannot adapt to the dense unstructured Indian traffic. That is for sure. Like no model can predict what is the traffic in India. So we cannot model it and have a answer for that. And no intelligent scheduling or interference management can be possible without AI and cooperative precision. And it is very difficult to accommodate large number of vehicles and the interference. So all this requires AI. So practical challenges of AI-based schemes are here. When we come into AI, there are some practical challenges. That is, first one is adverse weather, the camera visibility, LiDAR, radar news, GPS degradation. All this data, it will fade out and it won't be that clear. So what is the AI scheme going to learn? If the data is correct, it is going to predict. If the data is wrong, what it will do? So that is one of the challenge. Next is the long tail cases. As I said before, it is the rare, unusual, unpredictable scenarios like animal crossing, jaywalking pedestrians, unstructured Indian traffic, unique vehicles, odd roads, and everything. So to model such cases, the data sets are inefficient, and ML models cannot generalize such cases very well. Next is the validation. So you have a model, you have very well developed a model, how to test it. So this needs to be tested somewhere in a very heavy traffic, right? So millions of miles is one of the standard requirement. Diverse conditions, edge cases, sensor failure, what happens, extreme weather conditions. So the entire system needs to be validated thoroughly in every possible scenario. So one thing that comes as a help is the digital twin, like to form a digital twin network of the scenario and see how your algorithm is going to behave. It helps, but still that is a brutal task, and the validation is a very difficult task to do. And another thing is the testing, like hardware in the loop, software in the loop, how to do a scenario based testing and ensuring that the perception, prediction, planning, everything is accurate to a 99%. And the most importantly, it is the safety, like how the AI based scheme that I developed is going to be safe in all the situations. Like, how will I guarantee it? It should have zero false negatives. It should be fail safe, and fail operational designs should be there. And even if there are some sensor redundancy, communication, and everything, this algorithm is going to guarantee the safety. And there are standards like ISO and SOCTIF that say what should be the safety standard that is supposed to be there for the schemes. So those standards need to be met. So these are, I think I have said this before as well, why India needs custom solution. Even though we develop an AI algorithm, whatever is available in the US, we cannot use it in India because lane discipline is a problem. Unstructured traffic is there, and one another major problem is the side vehicle parking. Like even if road is there, like there will be some vehicle in the side. Then mixed vehicle type, we have two wheelers, cars, autos, trucks, mini vehicles, buses, everything. And in India, we have poor road infrastructure in many places. So if you have an autonomous vehicle that is supposed to work in a like highway, it when it comes to a city, town, or the junction, it is very difficult. And occlusions are there and inconsistent signage and signals. That is what I meant by roadside infrastructure. You don't have the complete connectivity to your phone itself. So to your car, if in case you require a complete connectivity, there is a problem. Then weak GPS is there and lack of HD maps. So in India, what can be done? So first thing is like AI must learn local driving behavior, like what a person is driving. So that is a important tick mark that needs to be satisfied by any algorithm that needs to be used in India. And it needs custom perception and prediction. Then robust localization is required without lane marking. The localization algorithms I said, mainly a major localization, the first step localization uses the lane marking, boundary marking, everything. However, the first step itself like may not be available in an Indian scenario. So what can be done there is a different problem completely. So what we need is India specific AV datasets and maps. So as I said, I am working in a wireless communication area. So I am using DeepMIMO dataset and everything where urban scenario is mapped. And when you need the data of a received signal at the car transmitted from a base station when the car is moving in a like in an area with 30 or 50 buildings, that kind of simulations are available. However, there are no data set or simulator or maps that give what is the real scenario or how your signal is going to be in India specific case. So then only we can try what is the problem with my model. This model is going to fail in this situation. Like we have an understanding that this needs to be done in India, then only it will work kind of thing. But testing is something that gives the confidence and that idea of how to develop the new layers and everything. So that is something missing in India. and tailored V2X, V2I communication setup, particularly for India, at least if in case we need an autonomous driving highway or a corridor that completely, say the straight highway from Bhubaneswar to Kharagpur, say, it will be like 6 hours, 10 hours, at least to that completes. It's a straight good highway, but without lane marking and everything. So that if roadside infrastructure is available, how can we make a setup for the autonomous driving thing? And one major application that people are looking for the autonomous driving is the industrial cases, like within an industry area, within the factory or something, for pick up and drop of the raw materials. So it's like sometimes speed doesn't matter much. They can move the raw materials in a slow fashion as well, but it's like many employees can like the pickup, drop, everything. If it can be automatized, it will be very much saving. So that is the other use case for the autonomous driving. So opportunities for faculties and scholars. I think I have spoke about many options that AI can do and what is the power that AI can bring in for autonomous driving. So one major thing that as faculties and scholars, even though we don't have access to many things, something that we can do is the creation of large India-specific driving data set. So that is something jointly we can do. Like if there is a module that is available and which can be kept in the car, so that even when you drive, those kind of data will be saved. And if such a data set that is specific for India is made, it will be very useful for all those who are working in the autonomous driving AI-based schemes in India. Then ADAS development for two-wheelers and mixed traffic. So those are like small changes that, like, sometimes if you can bring in some new parameters that is useful in a mixed traffic. So those kind of things are something that only research scholars and faculties can do, because these are not something that industry will focus on, even though there is a big impact. Then real-time multi-sensor fusion for unstructured environments. Then vision models for poor lane conditions and occlusions. Then localization without HD maps using camera and V2I and everything. Then AI models for Indian driving behavior prediction, like if in case you got the AI data, predict how that person is going to drive, or if he's like some people drive in the same lanes and people are very much used to changing the lanes very frequently. So that kind of behavior can be brought in. Then simulation and the digital twin development for Indian cities. Then safety framework suited for non-standardized roads. So I'll conclude the talk. The autonomous driving, which is one of the very highly developing area, and there is a lot of revenue coming in terms of the autonomous driving industry. You all know about Tesla and everything, like how much revenue they make and everything. So it's like people are shifting towards more, like I think most of our cars now will have the camera parking and everything. So this ease our driving and increase our like it is kind of like very easiness. It increases the easiness of driving and everything. So people are shifting a lot towards the autonomous driving. So if there is something available in the L3, I think the shift is of course obvious. And autonomous driving, however, relies on a tightly integrated stack. So an AI and ML is essential across all the modules in individual side and or as a whole as well. And classical methods cannot handle this complexity in India level, or also like in any area. If in case we want to move to the fully autonomous level, AI should come in. However, as said, the computational complexity, everything is a question. And as a person working in India, we have our own unique challenges like lane discipline, unstructured traffic, occlusion, mixed vehicle type, etc. So there is a large opportunity, research opportunity in all of these individual fields. With focused research, collaboration, and innovation, India can become a leader in affordable, scalable, autonomous mobility. So as I showed before, the two examples that I showed, like wiring one of the companies that IAC, that completely autonomous car, robo taxi available, and the next one is the by the Sattvic Robotics. So these are they have solved a very large problem and complex problem. So India is not far behind or something. We don't have it in the commercial scale because we are a developing country. So we have a lot of potential and we have a lot of opportunity in this field. And AI is something that is so much important and unavoidable. So as persons who want to work in autonomous driving, I think I would suggest that AI has a lot of opportunities uh, in both in the research opportunities and also in the startup jobs and everything. So thank you. Thank you for listening to the talk. I can take any questions if you have.
It was a very informative session, ma'am. Thank you. Now the participants can ask their doubts.
Madam?
Yes.
Yeah. Good evening. So it was really an informative session.
Thank you.
I have a doubt related with that vehicular communication, madam. So
Sure.
in a normal scenario where when we are driving through a road, there will be hundreds and hundreds of vehicles passing by, right? So
Yes.
in a vehicular communication scenario, suppose I think there is a lot of scope for optimization. Is there any existing optimization exists there so that that unwanted communication will be omitted so that the load can be further reduced for computation and all? Is there any future scope for research?
Of course, it is there. Like as I said, I am also working in the way to its area.
Am I clear,
So
ma'am?
my am I audible?
Hello?
Hello?
Am I audible, ma'am?
Yes,
Yes, ma'am.
yes, audible. So can I answer the question?
Hello?
Hello? Hello, am I audible?
Yes, ma'am.
Okay. So I'll answer the question. I'm also working in the same area. Like my problem is to the research problem that I am working on is like to maintain the connectivity when a
Oh,
vehicle is passing at a very high speed.
okay, fine, ma'am.
So I have one vehicle that is my eco vehicle. So that is what I'm focusing on. I want that vehicle to have the connectivity over the entire length of the road. So that is the problem that I am looking at.
It's a kind of
So
optimization, ma'am.
it is, of course, a kind of optimization.
Yes,
Like at the
yes.
transmitter side, every time I have a possible options of transmitting the signal in a like particular theta angle. So which
Yeah.
angle I should choose at each point of time is one of the optimization that we'll have to do.
Oh, fine. That's fine.
And another thing is like that is the case when one vehicle is running. When
Yeah.
there are 100 vehicles, how to form a signal at the transmitter? What should be the power levels that I should use for each of the vehicle? That is another optimization.
Yeah.
So the load and everything will of course come into an optimization problem, and you
Yeah.
don't have to like lose a user to serve another. So another condition will be to serve everybody in a fair manner.
Exactly. Fine.
Thank you.
Okay. Thank you, ma'am.
Sure.
Any doubts?
Hello, ma'am.
Yes.
Like you said that you try to ensure that all the vehicles, the communication link is not interrupted, right? While
Yes.
with the speed of the vehicle. So
Hmm.
there was a concept known as relay nodes.
Yes. Yes.
So can that be linked with some in some way to this?
Yes, actually, the 5G NR standard, that is the 5G new radio standard, what is supposed to be used by all the communication modules that is using 5G, they actually propose a option of using each node as like each car as a 5G node. Like if in case I want to transmit the signal to a user that is 1 kilometer away, I may not be able to reach that range. So I can use an intermediate car that is at half kilometer. I can use it as a relay. So transmit to that car, and from that car, it can be transmitted to the next car. So that kind of option is there in the 5G NR standard. You have the freedom to form such transmission data, that kind of packet and everything. So there is that freedom. However, at that point when you use some cars or some user as a relay, the problem is with the delay. Like instead of transmitting it in one shot, you're using two shot. So the first delay will be there. The received node sometimes needs to process it and then transmit. Or if it is transmitting directly also, the delay is anyhow going to be higher. For mission critical applications, like if in case you have to brake or the road is broken, you have to stop your driving now. So those kind of stuffs, if you use a relay node, then it will be difficult. In that case, you have to send it to the nearby base station to that car and then transmit it. So it will be application specific. The relay node thing is possible, but it will be application specific and message specific. If it is mission critical application, you won't be able to use it. But for other messages like to choose this path, there is traffic less. So those kind of things can be transmitted using relay.
Yeah. Okay. Thank you, ma'am. Thank you
Thank
for that.
If there is no more doubts, I welcome Ms. Suhaila, Assistant Professor, Computer Science Department, Majlis Arts and Science College, Paramanur, for the rapporteur duty. Ms. Suhaila,
Good
are
evening
you
to
there?
all.
Okay.
Myself, Suhela PP, Assistant Professor, Department of Computer Science. I'm here to present a brief rapporteur report of today's technical session titled AI on the Road, Opportunity and Challenges in Autonomous Driving was delivered by Dr. Rashmi P., Senior Project Engineer Research at the Center of Excellence in Advanced Transportation, IIT Kharagpur. Madam began by explaining the concept of autonomous driving and the global progress across the SAE autonomy levels. She provided a clear understanding of how AI is integrated into vehicles through sensing, perception, localization, prediction, planning, and control. She elaborated on the role of multi-sensor fusion, combining camera, LiDAR, radar, and V2X communication to improve accuracy and safety. The session highlighted real-world challenges such as weather issues, unpredictable human behavior, long-tail scenario, and the complexity of validating autonomous systems. Dr. Reshmi also reminded us that India requires unique, localized AI solution due to its diverse traffic conditions. She concluded by encouraging faculty and scholars to explore the research opportunities in autonomous mobility, simulation, AI model, and intelligent transportation system. The session was highly informative and insightful, giving us a deep understanding of both the potential and limitations of AI in autonomous driving. Thank you, ma'am.
Thank you
Next,
very much.
I invite Mr. Aguila, Assistant Professor, Department of Computer Science, for delivering vote of thanks.
Thank you, Sohila. A very Good evening to everyone. On behalf of organizing committee, I pleased to deliver vote of thanks for today's session. First, I express our sincere gratitude to Dr. Rashmi P, a senior project engineer, research IIT Kharagpur, for her insightful and engaging session on AI on the road opportunities and challenges in autonomous driving. Ma'am, your talk was truly enriched our understanding of this emerging era. And heartfelt thanks to Dr. Drishya Shashigaran for the warm welcome address and for guiding the session with grace. Also, thank our reporter, Ms. Suhela PP, for effectively capturing the essence of the session, and Mr. Sunish P for the technical support that ensure the smooth conduct of the event. Finally, a sincere thanks to all faculty members, research scholars, and the students for active participation. Thank you. Thank you all.